The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
We are the Hawaiian Volcano Education and Resilience Institute, HVERI for short. A lot of people know us from the 2018 eruption of Kīlauea in the Lower East Rift Zone. Working under Hawaii Tracker on the Facebook group. Since then, we've been trying to carry on and take the lessons, the hard lessons that were learned during that eruption and try and prepare for the next major disaster that comes to our island.
Yeah, and so we do that through two different programs. One is Volcano Education, and the other part is digital resilience, which we address through online groups on social media. So the way the two programs work together is that the social media networks end up being a distribution pathway for all the information. And having that network in place means we can provide more than just volcano education, but any other preparedness information as well.
What we were working for really came about in the Mauna Loa eruption in 2022. Within hours of that eruption starting, we had the mayor, Mitch Roth, we had USGS HVO Ken Hon on the stream trying to help flush out a little bit of the ongoing because it's so new. It's completely different from our previous major eruption, which was 2018.
One of the things that Talmadge and I were talking about was how do we deal with social media? And it was something we needed to figure out and get right. Our job is to get information to the public and make sure that the public get it as well as possible and as correctly as possible. When Philip and Dane started coming to and live streaming the meetings, it was great because we were reaching more people than we normally would. So when the eruption actually happened, we had this relationship. The interviews we did during the eruption, the most fun ones were the ones with Philip and Dave because they were more relaxed, and we knew we were getting to the local community, and people were asking questions. So those were the best. I think I just want to really give a shout out to those guys and how we worked as a team on this eruption. It really worked out well, and we got to a lot of people we wouldn't have normally gotten.
Aloha everyone, and welcome to our Hawaiian Volcano Tracker for January 8th, 2026. Happy New Year, everyone. We are HVERI, the nonprofit Hawaiian Volcano Education and Resilience Institute. And today we have a special presentation for you guys. I'm here with our ASL interpreters, Carrie and Dano as always, Mr. Luatori. Dane DuPont is with us on the back end, having done some work for us earlier in the day. Before we get to all that, Happy New Year, Lou. How are you today?
Happy New Year. It's going good. Going good. It's a good holiday and New Year around here.
Yeah, so yeah, and it was quite busy with the 1-year anniversary of our current eruption at Kīlauea, December 23rd, which also marked episode 39 of the eruption. And since then, we've been paused. And, the quick cut to the chase here is we're waiting something coming up in the next few days here, and we'll see how that comes about. But to be honest, we've been pretty busy the last few weeks here, taking some time off. So we're not going to bring you guys an episode recap of 39 quite yet. We'll just give you guys a brief summary of where we are presently right now. And we will play back for you guys the update given by Dr. Ken Hon, scientist in charge of the Hawaiian Volcano Observatory, delivered earlier today, just a few hours ago, over in Waikoloa. Anything to add, Lou?
Nope, just thank you, everybody, for joining us again. 2026 starts off. We appreciate all your support. Go ahead and throw your questions in here, and we'll try to answer them in the chat. I don't know if we're going to get back to answer them at the end of this stream, but throw them in there. It's Volcano Awareness Month, so we'll be busy, and stay tuned for more.
Yeah, absolutely. So yeah, next week maybe we'll catch up a little bit more and be back on track a little further. But we wanted to come back to you guys today still and share with you what the USGS is saying, as well as what we have happening now. All right, so yeah, here's a live view of what's happening now. It's been pretty rainy up here in Kīlauea Summit for many days now, and so not great visibility. Not a lot to see quite yet anyways. So that's just a little window into what's happening there. All right, all that said, let's turn to our volcano summary. And as always, Lou will be leading discussion, a chat, collecting some questions, and we'll see if we can not address them this week. Well, I will save them for next week at the very worst. All right, so let's get ourselves set up here. And it's amazing what just a couple weeks will do for making you rusty at this stuff. So apologies for that as well. And here we go here. Hello, everyone. This is a Hawaiian Volcano summary for January 8th, 2026. This is a current view of Kīlauea, steaming from both vents after several days of heavy rainfall at Kīlauea Summit. We have, in the last few weeks since our holiday coverage began, had episode 39 of the eruption, as you see in this USGS video here. That occurred December 23rd in the evening, lasting just under 6 hours, ending early in the morning of the 24th, with double fountains for much of the time, and triple fountains, in fact, as the north vent split into 2 smaller fountains during that episode. Highest fountains from the south vent were 1,400 feet, or 425 meters, with a total output of lava of over 9 million cubic meters, on par with some of the previous episodes, and covering roughly 60% of the crater floor. Here is another current view of our situation at the summit. Lots of hot lava flows that are hardened and solid, but retaining a lot of heat and some liquid inside, causing all this steam production. Looking at our ground monitoring patterns, here is the deflation signal from episode 23. I'm sorry, on episode 39 on December 23, and the re-inflation of the volcano's pressure shown through this ground tilt ever since then. We have a little bit of signal impact of rainfall in the last few days, but the current USGS window is between January 10th and 14th for episode 40 of lava fountaining. Everything remains quiet in both the East Rift and Southwest Rift, with all the activity contained within Haleakala Summit, as you can see through this recent lava thickness map released by the USGS last month. The main hazard for people still remains the VOG and the tephra. Here is the VMAP VOG forecast for the next couple of days, showing the aerosol layer drifting both northwards towards Hilo and southwest towards South Kona and Kau, covering large parts of the island with this variable weather. Combined with the rain, though, that can cause very spotty conditions. And so you see here a plot for Purple Air Monitoring Network focused on volcano area. And you can see that there are spikes and emissions coming and going across the days, depending on the conditions. So that still remains the main hazard, as we've had for many of the previous episodes. Earthquake-wise, it's been pretty normal. We still have South Flank activity with reduced activity under the summit, and Deep Pahala activity still ongoing for months and years now. To put this in some context, here are earthquake counts for the past year, summed up by week, and you can see not a lot of variation within this range of normal, which is what we've had ever since the eruption onset in December of 2024. So that's it for Kīlauea. We're just awaiting the next episode. We have had some overflows of the events today. So the forecast of episode 40 in the next few days seems very, very plausible indeed. Turning to Mauna Loa, which has also a new update from USGS released on January 2nd. They note the previous month's increase in activity, including a cluster of earthquakes northwest of the summit. But everything is normal as the volcano recovers from eruption and magma replenishes the reservoir system. If we look at the signals here, we can see that deviation that occurred towards the end of last year and a resumption that accompanied that resurgence in the volcano. So we're basically back on track with a little adjustment and variation that occurred towards the end of last year. This is the distance across the caldera, north to south on Mauna Loa, whereas the up and down signal showed a little bit more muted effect, but now continues rising as the volcano expands from magma continuing to fill it within. With its earthquake counts over the last year added per week, showing that spike last month, but back down again now. And in the context of the last 5 years, we can see that was just a little blip compared to the large buildup of earthquakes ahead of the Mauna Loa eruption back in 2022. So it continues to inflate. We'll await what comes next, but all is normal for now. And that's our Hawaiian Volcano summary for the week. Okay, so let's just quickly jump into some observations here. And I'm just going to show you guys the cameras to start here. Here's our V1 camera, which is showing a lot of fog there. Hard to see much through there. The V2 farther away sees pretty much nothing. And the V3, where we started off, is showing a little bit of that landscape, but just between the fog blowing in and out of there. So not much to see. I can add in here the thermal view from the F1 camera, which shows a couple of hot spots, but no major flows or activity through the fog there. And as I showed you before, this view from the B1 camera there over on the east side, showing all that fume rising from that hot crater floor. And we have Lou to add one more late breaking update here on our observations, namely that overflow we just had today. How about that, Lou?
Yeah, let's throw that up there. Just happened a little while ago. It's the first one, and we haven't had one since. I sped it up quite a bit because, the startup of the overflows, that lava was coming out kind of sluggish, so I beefed it up a little bit. But like you were saying there, Phil, the rain is just making the views amazing up there, honestly. But it's tough. It's tough. Had a little bit. If you stay here with us, keep watching, you're going to see the splution and splash and the gas kick up right as the overflow starts to end.
And for some context, we've had previous overflows last just a few hours and some last up to a week of overflows before the main episode of fountaining comes. So we'll trust the USGS signals, which they'll talk about in their update here, how they're doing their forecasting. And that is the best we have, January 10th to 14th. That would make it Saturday through Tuesday. Is that right? This coming week. And subject to change, of course, as always. And so we expect that next week we'll be recapping episode 40 for you guys. And then maybe the following week, we'll go back to 39 as we catch back up here and also insert some volcano awareness content from the USGS. So more schedule updates coming next week.
Yep. I also have one more thing, Phil, before we kick into Dr. Hon. And it's an update that just came out from the park. Go ahead and throw that up there. And it says closure is up there at Kīlauea Overlook. It's closed to protect the nesting nene family. There's a couple of them up there with some goslings. So know that the Kīlauea Overlook is closed. The closure includes the parking lot, surrounding areas, and the pit toilet.
The action is intended to prevent vehicle strikes and reduce disturbance to the birds. Not because of weather, it's because of the nene. I've already got a few questions on that already. So beware when episode 40 does happen, that before you get to Kīlauea Overlook, if that's where you're going, you may want to go all the way up top to Waikoloa, or somewhere else, turn around and head back.
Right, so that's really interesting, right? Because we've noted there's been traffic issues during these episodes of the park, one fewer parking lot for everyone to use. However, it sounds like the trail maybe stays open, so you could walk over to that area from the sides.
Sounds like it, right?
Yeah,
Just
not
vehicles.
quite clear here. But yeah, if you're trying to avoid vehicle strikes, then you probably don't care if people are walking. Although if you are in the area, certainly follow the signage and don't disturb the nene. Absolutely, right.
Yep.
All right, thanks for that, Lou. And
yep,
that'll get us ready, hopefully, for episode 40 coming up. It's business as usual for those of you guys who have been with us for the whole last year following this. And so we thought, given our break, the best source of recap and update would be the USGS themselves, giving their in-person presentation at Waikoloa earlier today.
Yeah, I got one more thing, Phil, before you kick on the video while you're setting that up.
All right.
For those of us here, we are lucky to get to talk to Ken on a regular basis and get to know him personally. And we've filmed him several times. This talk today shows his personality. His talk about one part of it, I'm not going to spoil it all, but one of them talking about the V3 cam and V3PO and the things they have to do behind the scenes and how they joke, and really shows his personality. He's a fun guy. So I just thought I'd throw that out there.
Awesome. Yeah. Something for our viewers to look forward to and to pick out from there. And we'll be here in chat following along with you guys. And all that said, we'll turn it over to our special presentation. And here we go.
And here's just the picture of the surface parts of our volcanoes, right? And this says active, but they're not really active in terms of being witnessed. Native Hawaiians undoubtedly saw Haleakala erupt, and it erupts, kind of a lot of its eruptions recently were up in the crater. And then we can see Mauna Kea, Waialae, Mauna Loa, and Kīlauea. Right, so those are the three that we've got that are active: Waialae, Mauna Loa, Kīlauea. And what else is what does Mauna Loa record hold for the planet?
Land.
That's close. It's very tall from the seafloor, and it's also the biggest active volcano on the planet. Right, and I'm going to use metric system in here because that's what I think of, but it's about somewhere between 50 and 70,000 cubic kilometers. So if you took bricks, a kilometer on a side, which is 3,000 feet on a side, there'd be 50,000 to 70,000 of those bricks. So what can you do with that many bricks? Well, it turns out you can go around the equator 1.5 times and make something that's 3,000 feet wide and 3,000 feet tall all the way around the earth. So if you were thinking about building your own resort island out here in the middle of the Pacific, you better get some materials together, right? But what does that tell you about our volcanoes? They're really busy, right? They are busy erupting, and they're putting out a lot of lava. There's no place on the planet that puts out more lava per year than Hawaii, right? And it is a hot spot. It sits out in the middle of the Pacific Ocean, away from all the plate boundaries, away from the ring of fire, right? It's as far away from a plate boundary as you can get. And it's something going on deep inside the earth, probably around the core of the earth and the mantle, the overlying rocky mantle boundary. And the plume rises somewhere around, 600 kilometers up through the earth, and ends up here and then melts rock underneath. Melt doesn't rise, but hot material rises. And as the pressure is released, then the material melts. So you can melt by heating them up. You can also melt things by reducing the confining pressure on them. So we don't usually see that in our normal life because we don't put things under that kind of pressure that it takes to make a melt not melt, right? So anyway, that's just kind of where we are and why we're here. And so our job at the Hawaiian Volcano Observatory, well, first let's get over to this If I can get rid of that little thing there. Okay. So this is the talk I'm going to give, kind of viewing the eruption that we've had for the last year at the summit of Kīlauea volcano from the Hawaiian Volcano Observatory, which is run by the U.S. Geological Survey. We're part of the Department of Interior, the same department that the Park Service is in. So normally our observatory has been housed within Hawaii Volcanoes National Park. But in 2018, during the Lower Puna eruption, the summit collapsed and the shaking for a period of a couple of months, there was a magnitude 5 earthquake every day. And the old buildings that were built in the anywhere from the early 1900s to the 1940s, which was the observatory and Jagger Museum, those things shook apart, right? And so they cracked, and the observatory building probably would have made it. It was actually finished. The new part of it was finished in the 1980s, but made the mistake of putting a basement into it. And all the pillars in the basement just shook and all the concrete kind of fell off of them. And the building had a crack in the floor, and part of the floor was tilted towards the caldera inside the building. So, well, it looked kind of intact from the outside. It was not a good place to be, especially if we get, does anybody know the biggest earthquake we can get on this island? So somewhere just above a magnitude 8 in 1868, we had an earthquake like that was focused down around Waiohinu, down around Naalehu, and the entire south side of the island moved about probably somewhere around 30 feet seaward in that. And it shook down everything fell down on the island, and palm trees were kind of almost touching the ground, the descriptions of them going back and forth and stuff. So you wouldn't want to be in a building that was already damaged here. And that's one reason why we have building codes and they're expensive, is because we get big earthquakes on kind of a decadal scale. But we monitor all the volcanoes here in Hawaii. We also monitor all the earthquakes here in Hawaii. And then we monitor volcanoes down in America and Samoa too. And we had in 2002, just before the Mauna Loa eruption, we were down there because there was a huge volcanic crisis where they were getting thousands of earthquakes a day. Just sort of showed up on these outer islands. And we know magma was being emplaced down in the ocean crust there. And it's kind of like the kind of eruption there would be kind of similar to the ones that were out in, what are the islands? Off Spain or off Africa that the Spanish owned the last few years. Anyway, they're pretty devastating. It would have created a thing kind of like Diamond Head, big explosion crater. And all the villages on those islands out there are inside of those explosion craters. So it was a pretty scary situation, but it calmed down. So since then, we've been monitoring that too. So here's just a picture kind of showing recent lava flows. These are in the last 200 years. The Hualalai flows are in blue there. The rest of them are graded by age, so they get warmer colors as we get toward the present. And the most recent flows, on Kīlauea are up in the summit in Halemaumau, but the big flows, this patch of red down in here, was the 2018 flows where the summit drained down to there. And then this is the 38-year-long Pu'u'o eruption right there, along with the little finger that went down to Pohoa. Okay, so here's a little picture I made using Google Earth to kind of get the topographic profile of Kīlauea volcano. And Kīlauea, if you go over there, it's kind of a, you feel like you drive up from Hilo and it's, The shield part is just a little wedge, though. It sits on submarine lava flows because this thing had to build up from the ocean floor. Magma comes up from way deep inside the earth here and feeds a magma chamber up inside the volcano, which is different than most volcanoes. If we talk about ring of fire volcanoes, the magma chamber is down in the crust below the volcanic edifice. It's not up in the volcano itself. Ours are housed up in the volcano. And the only way you can do that is have a lot of magma come through it so it doesn't cool off, right? You got to have a big high throughput of magma, otherwise the magma chamber would cool off. And we actually have a stacked magma chamber. We have a shallow one and a deeper one that's a little bigger. But as our magma cools, what it does is it drops olivine, that little green mineral. So when it cools, it comes up into that magma chamber, it cools, and it drops olivine. It drops it from this main magma chamber, and it drops it along the rift zones. So we have this very dense core of hot, kind of gooey olivine that's sitting inside the volcano.
And those push the volcano to the south, and that's what causes the big earthquakes and things, is the volcano is trying to slip and it gets stuck, and then it'll jerk like that. And actually, the volcano creeps about this much every year, both volcanoes, both Kīlauea and Mauna Loa, but they're still kind of stuck. And they're still, basically, you're pushing on a spring and storing energy in a spring, and sooner or later, that's going to overcome the friction, and it's going to jump. So the big earthquakes are related to the volcano itself. These little things in here, the long direction of the volcano, and this is a very long volcano. This goes down to 18,500 feet below sea level and 4,000 feet above. So the nothing kind of volcano that Kīlauea looks like is 22,000 feet tall. Not quite as high as Mauna Loa, which is about 29,000 feet from the seafloor. But it's still, if it was put on your plate, you wouldn't know what to do with it, right? It's a very large object, right? And it has paths that go all over through it. And Mauna Loa is much more systematic. It starts its eruptions at the summit, and they progress down one of the long arms that we call rift zones. And rift just means tear apart, right? There are areas where it's torn apart. Kīlauea can either start at the summit, be at the summit, or just pop out of one of the rift zones. It doesn't care. So it's more like whack-a-mole. The magma can come out almost anywhere. And our job is to figure out where the magma is at any time and make sure that people are out of the way of it if it comes out in a place that is populated, right? So that's where we have all these seismometers. We have instruments that measure the change in shape of the volcanoes. We have things that listen to the sounds the volcanoes are making. You know, we have gas monitors. We have cameras out, all sorts of stuff. This path that goes down real deep along the dense core in here is usually got lava in it, somewhere out into here. And that's what fed the 2018 eruption, is something out of the deep path down there. But if it goes all the way to the bottom of the seafloor and you pull the plug, that's below the bottom of this magma chamber. This one, if you look at where we were in 2018, someplace down in here, is about 2/3 of the way down that magma chamber. So that's the magma chamber we drained in 2018. But if we drain this in a big thing, that drains the whole caldera, and that's where you get the big hole that's up at the summit, or the big hole that's up at the summit of Mokuaweo'weo. Mokuaweo'weo's drain plug, though, is just above Hilo at about 3,000 foot elevation. And most of Hilo is built on the lava that poured out about 1,500 years ago from draining the summit of Mauna Loa. So while these things kind of look passive, like they're just sitting there, they can do some really bad things. And, you know, a lot of times they're doing really pretty things, but sometimes they can really turn around and do some bad things. So that's what our job is to watch, to try and understand the behavioral patterns that the volcanoes have, and then try and use the signals what we're listening to come up with a good idea that we can transmit to civil defense and the other authorities of what's likely to be happening in the volcanoes. So a lot of times not much is happening. Right now we're doing a lot of stuff up at the summit. And so here's a couple recent air photos of Halemaumau. And so this is Halemaumau crater, which greatly enlarged in 2018. These are the vents over here on the west side. This is the slopes of Mauna Loa. And you can see it's all filled with lava. There's two vents out there that we call the north and south vent. You can see them real well in this picture. Sorry, it's a little light in here, but this is the rest of Kīlauea caldera, Kalua Pele. And that's the rim of Halemaumau. So Halemaumau has been filled with fresh. It's actually filled in about 1,300 feet since 2018. So Kīlauea has been busy, and it's been extra busy the last year. So anyway, that kind of gives you an idea. There's Mauna Loa in the background. There's a little wedge of Mauna Kea. It kind of sits right back up over in here. This is a little picture to kind of show those two magma chambers. This is the high one under Halemaumau, and this is the deeper one that's south of the caldera. It's the Keonekakoi. There's Keonekakoi crater, or the South Caldera magma chamber. We call it either one. So this is the bigger guy in here, and this shallow one is smaller, but this is the one that's feeding the high fountains. Here's the vents right here. Here's Halemaumau right here. And then the bigger Kīlauea caldera collapses out here. This collapsed in 1500, right? Halemaumau really formed in about 1850, and then it greatly enlarged in 2018. So it's this size. And we're about halfway through filling it back in again to where it'll come back up to the floor of Kīlauea caldera. So in the last 5 years, we filled it about halfway in, about half a cubic kilometer of material has gone into there and filled it up. So one of the things we know about the summits of these volcanoes is they're the highest part of the volcano, right? What does that tell you about where most of the lava comes out? Somewhere around the highest part of the volcano, right? Otherwise, it wouldn't be the highest part if it wasn't lava coming out. But both right now, both Mauna Loa and Kīlauea have big caldera, big craters at the top of them. Are those things really natural long-term phenomena? No, at some point it's going to get busy and grow some more, right? It has to fill in that hole before it can grow. And in 1300, we had a massive shield volcano sitting here and another one sitting over here. And there was no hole in about 1300 AD. It was just two big shield volcanoes pouring lava out. One poured it to the south, one poured it to the east. So a little bit different setup than there is now. 1500, this current caldera formed, but we're filling it in. So one of the options of what could happen here is this could just go on and on and on in the summit here until we start building a peak back to the summit, right? There's a bunch of other options of things that could happen too. We're not so good at seeing the future. Here is the old Halemaumau that was there up to 2018. It was a very discrete looking crater. This really formed somewhere around 1850, but its current modern shape formed in 1924 when there was a big collapse up there. Here's the old Observatory and Jagger Museum complex right there, which is all now gone. It's all been removed by the park. And then here is Halemaumau collapsing. Here's the observatory for reference right there, the edge of the caldera out in there. So collapsing in here, the start of the enlargement of Halemaumau, and then this big deep is starting to form in there. So that is because we're taking magma from there, from that shallow magma chamber, and putting it out at Leilani Estates all over kind of the lower East Rift Zone. And as it went out, every day, a certain amount of magma would go out. This big block of rock sitting on top of it would look down and go, oh, and then go, thump. and that was the magnitude 5 earthquake every time it dropped because the magma was drawn under it. And it's going, I'm not supposed to be floating in air. And boom, it would bump back down, hit the magma again, repressurize the system. And it did that like about 50 times. So not a good place to live at that time. And here's the picture of the East Rift Zone. So these are the lava flows that came out as we drained the summit. And then I'm going to start a little video, I think, if things work out right here. So I don't know if we can see this, but this is going to show the collapse. So this is over a 3-month period. That's a piece of the road that just went down. So that was kind of what happened in 2018 when we take the magma out of the system. This next one shows us filling it back up. At first it filled with water, and now since 2020, it's been filling with lava. So boom, 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 here we are filling it back up. Now, the deep part of that was kind of like an ice cream cone. So it filled up really fast because there wasn't a lot of volume down in there. But then as we got up to the shallow part of the collapse, it's really broad. So there's a huge amount of area. So it's going up a lot slower because we have to spread the stuff out over a big area. But kind of hard to believe. But it does make you believe the Earth does change shape. You know, we don't see most of it because it happens on a time scale that's so large. We don't see continents drifting around and doing all that stuff. But here in Hawaii, we can see these kind of big landscape changes that happen over very short periods of time. It is on our website, but our website got taken over by the central part of the agency, and searching for things is no longer easy. So yeah, these videos are out there, but they're not necessarily, you have to do some searching for them. So if you search for the time-lapse collapse of Kīlauea, yeah, you'll probably find it on YouTube and places. You'll find it in a bunch of different places, I think. But okay, here's a little cross-section we've made. This is the old ground surface right here with the original Halemaumau right there and the edge of the caldera over here. And so this deep hole formed where right underneath Halemaumau, and then this shallower hole formed, and that's because the magma chamber down at depth down in here goes all the way across this area right in here. So when stuff came out, it caused that to fall, not just the central part under Halemaumau. This shows filling that crater with the lava lakes that we had up through to 2024. And then this is the last year of eruptions, these high fountains, and they basically poured lava flows over the top of this lava lake. This in here is still molten. And every once in a while, we see some of it come out. It's easy to tell because it has a different set of crystals in it because it's been cooling for a while. Then I put the conduit on here. So this is the path that magma is taking out from the magma chamber, which is down about here. So it's sitting down there and that taps in there. And the important thing is that the starts of eruptions start off as cracks. All Hawaiian eruptions start off as a big crack in the ground. As the pressure from the magma pushes up, it fractures the rock and it comes out in what we call a fissure eruption. A fissure is just another name for a crack. You know, crack eruption doesn't sound that good and it could be confused with some drug paraphernalia or something like that. But the fissure eruptions, they used to be called curtains of fire, but people sort of took offense because nothing was actually on fire. Unless you're standing there, you will go on fire. But the actual rock is just molten and radiating light, right? It's so hot that it's radiating light off of it. But so the thing you have to have is the crack has to cool off. And we'll show you a video of it doing that, but the crack cools off at the narrow parts. And to get these kind of high fountains, what it has to do is focus down on a couple of the wider parts and make basically a cylinder like a gun barrel. So these cylinders, we got two of them that go way down, and we don't know if they independently hit the magma chamber or if they connect someplace at depth and hit the magma chamber together. But there's two very straight, narrow chambers that go down, and I'll explain why that's important. And they're only about 10 meters wide, about 30 feet wide, each one of them. So the crack was about a half kilometer long when it started, and then it focused down on these things, and within a couple of eruptive episodes, it had made this gun barrel kind of structure. And so in here, we need water-rich magma. So when you're making one of these at home for yourself, we need a narrow nozzle-like vent. We need to have the magma rise faster than the bubbles can form. And if you have a big vent area, it means the magma can come up slowly, right? It's like, think about a garden hose. If you have a hose, it comes out a little faster. If you cut a big slit with a razor blade in the hose, it's going to come out a lot slower, right? And the fissure is kind of like that slit. So it's going to come out slower. It's going to rise slower. When we make it go through this little nozzle that's only 10 meters wide, to get the same amount out, it has to move faster, right? And that faster, what it does is it moves up faster than the bubbles can form. The bubbles would normally form someplace down in here, but the bubbles won't form till about up in here this way. And then you get an expansion of about 100 times when the bubbles form. So it turns into a foam, and that shoots stuff out of the top. So a couple of things that we have to get is that initial velocity, and then we got to get the foam forming. So again, nozzle-like vent, and we've got a couple of them. We got 3 of them right here. Expansion of gas. Okay, similar to a soda bottle, and I'll show you the pictures of if you haven't ever seen the Mentos stuff, it's not that different than a Mentos kind of experiment. And when the vent gets angled, like this was episode 38 when we lost the camera, it angled to the side because the south and east sides of the vent basically exploded when the amount of magma coming through them just increased to the point where the vent was too small, so it blew up the sides and then it tilted over. So here is a regular garden hose. So stuff is coming out. It's not coming out that fast. put a nozzle on it, right, that increases the velocity of the water. And the same amount of water has to come out in the same amount of time. And we've all watered our lawn, right? And kids always put their thumb across it or something like that. You can remember when you were kids, can't you? I don't see any kids in here, but how many people can't remember when they were kids? I'm kind of close to that. But at any rate, you have brothers or sisters, you'd spray them, right? And that's what you're doing, is creating a nozzle so the velocity of the water has to increase. But that by itself is not enough. You've got to then have the bubbles nucleate instantaneously. You don't want a slow nucleation of bubbles, because then the bubbles can rise faster than the magma does, and they just pass out as gas up at the top. So what we want to do is do something, and when you do the Mentos, or this guy's going to dump baking soda into his Coke, what that does is cause bubbles to nucleate and form really fast, right? And the same thing happens when normally these things happen at about 1,500 feet, the bubbles will start nucleating. Not 1,500. Yeah, 1,500 feet. Water will start coming out just like soda bubbles of carbon dioxide come out in your carbon dioxide in your soda. And if you ever shook up a big bottle of soda and release the cap a little bit, you'll see bubbles start to form, and then you twist the cap back again, you put the pressure back on it, right? So you're regulating the pressure, and you take it off, you get sprayed, right? You shake up the can and open it up, you're going to get sprayed, right? Because you've agitated, that also nucleates bubbles, the agitation. So a lot of different things. This guy's going to dump some stuff in here. So let's watch him dump some stuff in here. So it's got a nozzle, it's got a magma chamber, and look, this whole thing is turned to foam, right? All the way inside there. And what happens is the weight of degas magma is holding the gas-rich magma down at depth. So before these eruptions, a lot of time we push out a lot of denser degas magma, and that magma comes out until we get the gas-rich magma up to the surface that can start forming the bubbles, right? And once those bubbles form, though, the weight of the magma column gets lighter, because all of a sudden it's expanded by 100 times, so it basically weighs nothing. So that area where the bubbles are forming starts to migrate back down into the magma chamber until the whole magma chamber goes, or the top of the magma chamber goes. And that's why we get these big high fountains. So everybody got that? If I give you a test on that? So there he is doing it again. I did this once with my, I did it a bunch of times with my kids' class at the elementary schools. And I had some Diet Coke that was like in my garage for a year, one of those big bottles. So I went out and put the Mentos in it, and it made a fountain about this big. So then I asked for a volunteer, and this kid came up and, you know, said, okay, and would drop the Mentos in. And they just stood there watching. And they weren't ready for the fountain, came up like this and all over the place. But luckily it was diet, so it didn't like turn into a sticky mess, and the kid didn't end up with ants all over them for the rest of the day. But okay, so that is some of the foam right there that we're holding up out there. And there's so much loose stuff when we're out in the field, we have to wear both gas masks and face shields to keep all the little glassy ash particles out of our eyes. This is a bucket of foam, which I'll let you guys play with later, but there's a piece of foam. And this stuff weighs almost nothing, right? This has been carried up as high as 30,000 feet and dropped miles and miles away from the vent because it's so light. So if you get enough hot air, these things can go way up like little sails and go up in the air. But that's what happens to what was dense magma. It has less than 1% water in it, but that 1% water turns into 98% bubbles. So we get about 100 times expansion of the stuff when it goes out. And that's what forces it out. You probably want to see some of the fountains at this point instead of just hearing all this baloney about how they form and everything. You can tell what I'm interested in. I'm like, the technical details are interesting to me. But this is looking down in the north vent. The south vent is right behind it. But that's kind of looking down in the conduit. We don't get many good looks down in those conduits, and we can't see very far down in them.
What is actual gas? Talk about bubbles.
Water is what's generating most of the bubbles. The gas that annoys us is sulfur, but it's very much smaller proportion. It adds to it a little bit, but basically our volcanoes are giant steam engines, and water is driving these eruptions, and that's what forms most of the bubbles. And a lot of that stuff that you see coming out in the plume is magmatic water from deep inside the earth. So maybe we ought to bottle it and sell it you know, deep water, like you sell this like deep water offshore of Kona here and all this stuff, deep ancient water. Well, this is coming from hundreds of kilometers down inside the earth and coming out. So if you can condense that and maybe make it taste a little better, maybe you could make a mint off of this. I don't know, but all that white stuff is magmatic water coming out of the system. So when you see the white color, that's almost always that. And it depends on the dew point, how much it is visible, right? So it's one of those things you have to study physics to understand dew points and those wet bulb thermometers that you whip around and all that kind of stuff. I never figured that out.
Sure, make any difference at all.
So the volcano, it does not care. Yeah, it's all about pressure and heat from the inside. So, and what these things are regulated highly by pressure.
The water comes from the rain.
No, water comes from the early earth. So this water, and also from stuff recycled from the ocean that gets taken back down in the mantle at subduction zones. So this is water that is very much bound with rock at depth, right? So it is not rainwater. Rainwater can cause some issues. Sometimes we get little explosions or a little bit of stuff, but this stuff that we're seeing in here, all the steam that's coming out of the vents is generally the magmatic water. Now, if it's really rainy, some of the rainwater will get in and heat up too, and it'll add to it. But okay, so we measure stuff out there. That's our job. Go out and measure. And people complain, why are you out there? We're out there measuring stuff. So we try to get out there and measure the fountains. We can measure them off of our cameras. We can put scales on the cameras. They're kind of not super accurate. But here's kind of the measurements of all the episodes up here to 39. And blue is the north vent and red is the south vent. So they're added together. The highest fountains were here in episode 35. They got up to 1,500 feet. And that allowed us to join the 1,500 foot club. There's 3 other eruptions like this. Kīlauea in 1959, Mauna Ulu in 1969-1970 that had high fountains, and the start of the Pu'u'o eruption from 1983 to 1986. The highest fountains recorded here were in the 1959 Kīlauea eruption. They got up to 1,900 feet. But everybody else got up to, at least had one episode that hit 1,500. So we finally made that. We started off with kind of smaller fountains, and it's really kind of remarkable because we have twin fountains going. Only Mauna Ulu had twin fountains, and only for 4 episodes, and they weren't particularly high. So this is really remarkable that we have 2 fountains going at the same time, and we can hit those kind of heights with these things. In here, this is looking at the fountain heights with time, and we can actually take this along with the pressure. We measure the pressure by tilt of the volcano, how much the volcano is tilted up. And we can do things with calculus on the tilt, and we can get rates of how fast the magma is coming out of the ground in these things. And we actually have been able to figure out by that the volume that's coming out too. So you can kind of see we've had pulses where it kind of drops down again, pulses again, drops down, pulse again, right? So there's different things going on in there. We don't totally understand what's driving those dynamics. We hope as we study it more, we'll get a better understanding. But you can see there's 4 graphs for how the fountain heights behave from the north and south vents from different episodes. And you can see there's quite a bit of different behavior. It's also things that we would like to know why it behaves differently.
I have a question. If we have a
just a sec, let's play this and then we can have a question. Since I already started it. This is the start of the eruption. It's fissure. Lots of lava coming out of there, right? Okay, and watch what happens with time during this. How many vents do we got? 2 or 3, right? At the end there. So now if you look at it during the day, there's only 2. So this is actually, this thing necked down and formed those 2 cylindrical vents really fast. And they're very close together. We can't really quite figure out how these things were sustained, and they're only about 150, 200 feet apart or something like that. So they're really close to each other. Question, who had the question?
you can do that, if you're kind of monitoring your website cameras.
Yeah.
You say that, and I know it's a
Well, I'll show you how we calculate that. There's simple ways and there's complicated ways, and it's as much art as it is science. But a lot of people just, well, we'll talk about that. I've got a slide in here about that. So okay, here is the family portrait. So you can see one from everybody, right? So we've had two vents that continue, even though some of them have, like for a while, the south vent just disappeared and then the north vent disappeared. And typically these things are fairly like in the 6 to 12 hours, but they've been as short as 4.5 to as long as 8.5 days long. So there's a lot of variance in that. But recently we've had a lot of volume come out, and most of these eruptions have only gone for 6 hours. So we've had really high effusion rates during those periods. So maximum lava fountain of 1,500 feet, plumes up to, they're actually over 20,000 feet. The Weather Service measured the episode 38 plume at close to 30,000 feet. And it got up into the westward flow. The top part of the plume, the lower part of the plume went southwest towards Pahala and over to Ocean View. The high part of the plume went due east and out over Puna and about 100 miles out to sea before it turned south and kind of dissipated. And that was above 20,000 feet. And that, we went down Chain of Craters Road, miles from the summit there, and there were tephra bombs being dropped out of that high thing up above 20,000 feet. There were these reticulite bombs, these really foamy tephra bombs, dropped onto the road and stuff and hung in trees and things like that out there. The best place to look for them is in trees now because they shatter when they hit the ground. And then people drive over them and everything. So very mean. Okay, so all the lava flows luckily have stayed in the crater, but the ash gets around, and depending on what the wind conditions are, it can end up in a lot of different places. Okay, so this is going to be the video recount of the whole thing. We tried to do this as high, oh, we'll watch it. So this eruption, you can get an idea from just looking at it set in motion like that. This is a historic eruption. Probably it's going to be the most famous eruption in historic times of this volcano. And it's really visible. The park has made it so people can get up there and stand on the rim and watch it and hear it. And if you haven't been up there, try to get up there. And we'll talk about how you can figure out when it's likely to go. So anyway, it's an amazing thing. We're blessed to be in this time where the Kilauea Iki had 17 episodes in 2 months in 1959. Mauna Loa, or Mauna Ulu, had 12 episodes in about a year, so about 1 a month. Pu'o'o had 44, or really, if you want to count to the start, 47 episodes in 3 years. So it was a little over, it was about 22 days apart or something like that for those eruptions. And now we've had 39 in 1 year. So we're doing 3 eruptions a month, which tuckers us out, quite frankly. So we stay busy. What does what? A high fountain episode. In between, we call it precursory activity when it's shoving the degas lava out. It's going to be part of the episode, but it's the precursor to it. We're measuring, the only thing we can really predict is the onset of the fountains. The onset of precursory activity is really tough to deal with. And so we separated that out because we knew I lived through the Pu'o'o eruption and everything, and that's what we did there, and it works really well. We just are looking at the high fountain part of the eruption. We record all the rest of it, but it's when that fountain starts, that's what we're looking for. And that's what everybody else is looking for too, because they'll go up there and they'll see lots of lava pouring out, and people will go, well, when's it going to erupt? And it's like, that is molten rock from the center of the earth coming out on the surface right now. That is an eruption. Yes. But it's not the eruption I was looking for. Well, we're pretty accurate here because it's inside of a big hole, so it can't get anywhere. When it's out on the ground, then we use topographic models, and the topographic models have to be continuously revised, right? So we can be pretty accurate with that. The flatter the ground gets, the less accurate it gets, and the earlier lava flows then make blocks and change the direction of later flows. But on things like Mauna Loa, where there's very steep slopes and stuff, we can pretty much nail where it's going to go. And we have really complex models that have to be run on. USGS has a supercomputer, so we run those models on a supercomputer to get where it's going to go, how long it's going to be there. We put in the properties of the lava and everything like that. So we're getting pretty good at that. Okay, so this is just showing this getting rid of the degas lava before the fountains start, right? So we got to get rid of all this heavy lava that's holding the pressure in. Oops. I can start this. So you can see a little bit of blurping going on beforehand, some spattering and stuff. And then we start to see little overflows. And sometimes, I'll tell you that in a second. But we start seeing these intermittent overflows, right? So this is what we call intermittent precursory activity, where it's not continuous. And then boom, it goes right into that. So in order to tell when the fountain's going to happen, we look at what's going on, and there's two ways that in the precursory activity, most of the fountaining, the little fountains, occur when lava drains back in the vent, and we get gas release during that. Those are not fountains that are telling us it's about to happen. What we're looking for is fountaining as the magma is rising in the vent. If it starts to fountain, then that tells us gas, fresh magma is coming up, rather than just taking stuff back down in the vent. The other thing we look at is we look on our seismometers for tremor, and we look at a crossover between the tremor and the tilt. And so we have numbers that, so we're looking mathematically for numbers of when the tilt and the tremor crossover, and then looking at that with the fountain behavior. And that's how we're calling the starts of these things. And so we can see when, you know, the fountain may only be 30, 40 feet high or something like that. That's what we can actually call the start of that episode based on looking at our instruments and looking at this. It takes, you know, you got to watch a lot of them before you know what's going on, but you can eventually kind of get a feeling for it. So this is what happened. We're getting rid of the plug in the champagne bottle, which is this heavy magma that's sitting in that big, deep cylindrical vent. You got to push that out. Then the water-rich magma can start to rise, and the bubbles can start to form, and then we get the fountains. Sure.
Versus tremors. Is a volcano going to cause earthquakes because of the pressure coming up and the lava all over?
Like at the start of this eruption, yeah, we were tracking earthquakes for the start because a fracture has to form, and that fracture has to move to the surface. And so as the rock breaks, it generates earthquakes. But now that we have an open hole, what we're seeing is tremor. And what that tremor is gas expansion and contraction down in the magma chamber and in the conduit. And what that's doing is it's expanding and contracting constantly and vibrating the ground around it. So these are more like vibrations rather than breaks that go like that, right? So we have different ways of looking. There's a bunch of different kinds of earthquakes, and that's why we have smart seismologists. They're really good at looking at all these bizarro waveforms that come out there. And there is a lot of them. We have many, many different kinds of waveforms that we look at on our seismometers. And they have a lot fancier access to data and the screens that they look at it than what goes out on our public website. So they're able to look at a lot more detail, but you have to really be trained in the waveform and waveform analysis for that. So this is the tilt record. Down below is kind of a look at the first 16, and it's a little blown up. We measure the tilt of the summit, and it's basically, you can think of a balloon. As you blow it up, the summit will kind of tilt away like this of the balloon, right? And then as you shrink it, it'll go back in like this, right? We measure this in microradians. Everybody remembers what a radian was, right? Radian is that thing that mathematicians use instead of good old degrees, so like 360 degrees, that's a good thing, right? And we can do the degrees of tilt, but you actually can't measure degrees out here. So what you're doing is radians are kind of there's no real dimension to it, right? So they're really, how many radiuses? There's 2 pi r radiuses around a circle. So, as the thing goes up, we can use that as an angular measurement too. 1 microradian, just for reference, if you had a 3,000 foot long 2x4, 1 microradian is putting a dime under one end of it. So these guys are pretty sensitive, right? We can measure down to 1/10 of a microradian on these things. So we look at that stuff, and you can see the initial, right in here, where the initial eruption and fissure started, and then a drop, right, as magma came out. Then more magma came in, another drop, more magma comes in, another episode, and a big drop, and then we kind of start the regular episodic fountains after that. And notice the drops are not all the same, right? They're really different in different places, especially early on as this thing is getting started. And they're kind of related to fountain height, is what the shape of the drop is. And what you can't see in here, these drops look like straight lines. They're not, they're actually curves. And we analyze those curves. We take anybody like calculus in here? We take the first derivative of those curves and look at the change in the thing on there. So, and that's how we can tell the rate of stuff coming out. This is all of the episodes in here. And at first they kind of came down here and fit a curve. Then they were kind of flat. And now you can see the peak is descending. So when we did this, fits into our forecast, we have to account that it's not going to make it up to the last peak. So we have to mathematically model where it's likely to be. And that's not always easy. It's a bit of a guesswork job and sometimes. Here is looking at these and changing these drops into volumes. And so the highest one we had was episode 38. That's the one that took out the camera, the famous V3 cam. We tried to name the new one V3PO. But the guy who runs the camera network said, that's unprofessional. And we said, well, it's the V3 camera that's been permanently offset. And that's what the PO was for. Of course, it was to make it sound like, because everybody like on the web, everybody like, oh, the V3 cam. Oh. And the little cameras, they actually look like minions, the one-eyed minion, They're very adorable little cameras, But we weren't allowed to we had V3PO in an explanation for a while, and we had to take that out too. But so there's an inside bit for you guys. But anyway, that one was the highest diffusion rate in a short period of time. This was 6 hours. This is the one that went on for 8 days, so it's got a high diffusion rate, but it's very slow compared to this one, right? It came out really fast. And this is modeling the diffusion rate from the fountain heights. And this is in cubic meters per second, 200, 400, 600, 800, 1,000. So this was episode 38. So it came out at 1,000 cubic meters a second. So anybody know what a cubic meter is? About a cubic yard. It's a little less than a cubic yard. Anybody ever had dirt delivered to their house? One person, that's it? God, you guys buy these places already landscaped over? You guys live the life over here in Kona, don't you? All this stuff, like this grass just grew over the uplands out here. Got to have big trucks, semi-trailers full of stuff, right? And you get like 20 cubic yards of something, right? Imagine this, 200 cubic yards, right, would be 10 of those trucks every second. That's about what went out in 2018 of those big semi-trailer trucks full of stuff, right? And then 1,000 cubic yards per second is just crazy, right? But that's what, when you make that much come out, there's a lot of heat that comes out, and that's what drives those plumes way high up into the atmosphere, is there's so much heat that it's causing the air to convect up around them and drive stuff up really high. So you got to have a lot come out, but it's got to come out really fast, right? And then we'll make the big plumes. And so we can actually measure this During the eruption, this is all one fountain, right? From here to here is one fountain, but this is the instantaneous effusion rates. And then we can measure the average effusion rate, which usually comes out around 200 cubic meters a second for an average of the whole thing, which is about what it did in 2018 was the constant rate, and also about what the Mauna Loa eruption was doing, about 200 cubic meters a second. The normal rate of stuff coming into the magma chamber from the deep in the earth is about 3 cubic meters a second. So a lot less. And over the last year, because we've had a lot of stops between the fountains, the average is about 6 or 7 cubic meters a second. So about twice the long-term average. We're using excess magma that was stored in the prior year, the year of the earthquakes at Kīlauea Summit, if you followed that stuff. But there was a lot of magma pumped into the deeper magma chamber in 2024. And we're using that to sustain these really big high fountains and get all this volume right now. Okay, so here's how we predict. There you go. Easy to see, right? So you got to do two things, right, to predict these things. You got to know where you're trying to go with the inflation, right? And you also got to know is how fast is it getting there? How fast is the thing re-inflating? So we got to know how big are we blowing up the balloon and how fast are we blowing up the balloon, right? So this blue line right in here is looking at the change in inflation and fitting a power law curve to it over time. And that gives us an idea of looking at all the data, how fast the magma is coming into the system. Notice it's changed. It diverted off. The red dashed line in here is I force it through that point. And these are days since the last eruption. So, you know, if you follow the blue line, this is just getting back to where the inflation was. This is using those 6 last eruptions out in here. So we get a wide variety of answers from these things, right? And we actually have we have 4 different models that we're using, and we're kind of look at the results of 4 different mathematical models. Some of them are Bayesian statistics, and some of them are random generated models and stuff like that of looking at things. So this is done by randomly generating a bunch of tilt models and looking at the peaks where these things, and this is using all the summit tilt meters. This only uses the one at Uikahuna Bluff. So there's a lot of different ways to do this. And, you know, that's why, you know, you could say, if I believed it was that, I could just say that day, 20 days from the start of the last one, that's where it's going to be. But these are kind of error bars around them. And then this one here. So we get a really wide range of answers in here, depending on what model. That's the kind of the uncertainty built into this. So we can't say, you know, at 11 o'clock p.m. on Monday is going to be the start of the new one. We can get those numbers for you, but with all the uncertainty, they don't mean anything. You know, every one of these models generates a number like that. But, you know, we put it out in ranges, usually of 3 to 5 days or something like that is what we're looking at, you know. So right now we have this kind of unpredictable slowdown, and those are hard to model because it's clearly not fitting the mathematical model that we had. So it's slowed down the amount of magma coming in there. We don't really know if it's going to hit this green line. That would be the earliest it could go. This would be the latest it could go, kind of in there. So we have this, we're always kind of fudging the forecasts around to understand it. So it's not just as simple, it's got to get back to where it was before. And you also have to know how fast is it going to get back to that, right? So anyway, that's what we're doing with to put the forecast out. And if you don't have, we have these messages we send out, updates every day that has the renewed forecast in it every day. So those come out, and I think a little short part of it goes out onto Twitter. What comes out of there? This tephra comes out, which is the foam, right? This really light tephra in here. We also get lots of Pele's hair. We get lots of fine ash. We get more dense tephra. And around the vent, this is Pele's hair right in here, right around the vent, we get very dense molten spatter that lands. And most of that then turns back into lava flow. If it's further away from the vent, it welds together into solid rock with no bubbles in it. So that's what happened to the poor V3 cam. It was sitting in a place that fountain turned sideways on it. It got buried by 50 feet of spatter that turned into solid rock. It's not like it's like 50 feet of this light cinder that you can shovel and look for it. No, and whatever is in there, it's solid glowing rock that stays hot for weeks. And so whatever is in there, we dug something out of that kind of stuff once, And this guy who had done this experiment really expected to find his little microcomputer and the battery and everything. There were a few little lead fins, and there was a hard drive still there. It was all mangled and rusty looking and bent to pieces, and he picked it up and he was talking, he goes, well, I was hoping to get some data, and some little white ashy things fell out. One of the other guys goes, well, there's your data. There goes your data right now. That came out of the thing. So there is nothing left of anything that gets buried in this stuff like that. In the finer cinder that isn't red hot, you could get some stuff, but a lot of that is also hot when it's in place. So this is looking at a plume in here. So the fountain, this fountain was up at about 1,200 feet. And then this is the plume that's going up, and you can see this dark stuff. That's the ash and stuff that's being carried into the plume. And this one went up, and then it split into two plumes. One went southwest, the high plume went southeast off of this one. And this is a thing that we use radar satellites, and we can measure the change in thickness of this tephra between episodes. And so the light green stuff, we do this after every episode. And here's the vents over in here. And this shows us where the lower plume went and deposited most of the tephra near the vent. So we're building up a cone up here, a lot like the Pu'upuai, which is the cone at the Kīlauea 1959 eruption. You go up and look, it's a long sloped affair that goes from Kīlauea to the south. So we've got a cone like that. The difference is we still have the caldera cliff in here. I'm still waiting for it to be completely filled up, so there's a continuous vent structure built between the rim of the caldera and down in the caldera. Okay, and this is the nice way of saying this was the end of the V3 camera. Thank you, V3 camera, for recording this, because this made its rounds very rapidly around the internet. And people posted many nice messages about the end of the V3 cam. But so that's all fine ash. As the plume was hitting, it was all this fine stuff was breaking into pieces and the hot air is taking it up. And then you'll see the vent turn over sideways. And the stuff that's in that big rising fountain is starting to come closer and closer to the camera. So you can see a lot of that stuff is orange coming down. It's molten. It's like got the consistency of Jell-O, but the weight of a rock if you get hit with it. And it sticks to your skin. So you don't want to be out in this stuff. And those blocks coming down are like this size to this size. They're not little teeny things. They're not little fist-sized things. They're things like this. We'll see them as it gets closer up to the camera here.
How far away camera?
It's about 1,500 feet from the vent. It was up on the rim of the caldera, so it was in a place that hadn't been hit yet. And there's the big stuff coming in. Yeah, now it's just getting smashed with stuff. And there's its last little feeble call for help. It's like, help, I've fallen and I can't get up. And we spent a lot to get a new camera out there because these things are obviously really watched by people. So we made sure we took our priorities and we built. These things are not easy to get out there either, because we have to fly them out with a helicopter, and they have to have solar panels and batteries and a whole bunch of electrical stuff to run them. It's like a little power plant that's out there for each one of these cameras. The cameras aren't that expensive. They're like a couple $1,000s, but the whole thing is quite expensive, especially when you consider the time and then the flying them in and out of there and stuff. So they're not something that's easy to do at home. So we have solar panels and batteries that all go together and they hook underneath a helicopter and they can just lift the whole thing up. We built these special custom racks that take the whole power supply unit out there too. So yeah, so we have a new V3 camera out there. I don't know what time it's getting to be here. 2:32. So I've got a little bit more to go through if people want to sit and go through it. Okay, otherwise people can take off if you have things to do, and then I will stay around afterwards. So other things that come out besides the tephra are lava flows, right? So we get lava flows before, but we also get these big lava flows during the eruption. All the rest of that spatter that comes down turns into these lava flows. And by the time they make the kilometer across the floor of Halemaumau, they've generally turned into something a lot like a'a. They start off as kind of pahoihoi near the vent and then turn into a'a. And then up near the vent, things get covered with cinder. And this weird looking thing in here is covered with some of the light cinder, but it was a lava flow where a bunch of molten spatter landed up on the up above on the cliffs and made a little lava flow that went there too. And we're also getting all sorts of lava that gets stuck on the cliffs, and that stuff will continue to move for days after each eruption. It just goes downhill, and it looks like a glacier. There's all these big cracks and crevasses and stuff like that in it, and they're really large. But almost everyone has done that. So we also get a lot of gas, and we work with the University of Hawaii, who has this thing called VMAP, which is the VOG tracker. So you can track SO2 and SO4 around the island. So if you're wondering why you can't see, you can go on here and look, and you can kind of see this concentration of stuff over in here. And that a lot of times it comes around Mauna Loa and hangs out, right? But there's a lot of gas coming out of here. During the eruptions, the rate of gas coming out would be about equivalent to 50,000 to 100,000 metric tons of sulfur dioxide of a gas. So like just try to get 1 ton of a gas. I mean, it's not easy to do, but 50,000 tons of gas come out in these things and maybe more. So on this side, it just depends. If people have, it can exacerbate health problems. I'm not a doctor, so I can't really say. It's generally, we've found it's not good to breathe. So that's why we wear gas masks when we're out close, but the concentrations are way higher, and we have to wear little gas detectors. So if we get more than 5 ppm, then we have to leave the area immediately. So we have a little gas detector that each one of our guys has when they're out there, along with all this protective gear that we wear when we're out there as well. But it affects people differently, and it certainly affects the view. As you notice, everything is foggy. Why did I move to another LA? So here's what you'll see when you go to the website. It just shows the little pattern of it going up. There's other there's GOES satellite images that you can track the plumes and things like that with. So there's a lot of interesting stuff. So water vapor we don't see. The sulfur we do see. Water vapor we don't see because there's lots of water vapor in the air. So it's basically invisible unless there's a big plume, and then you can see it on the radar. The Weather Service radar will see that. So these things, we want to make sure that pilots are aware that this stuff. So we call the Weather Service, who talks to over in at the Daniel K. Inouye Airport over in Honolulu, and they talk to the FAA that an eruption has started, and plumes may go up as high as 20,000 feet or so. And you can see the ash in that plume there. You can see this stuff above the eversion in here is still going up. It has less ash in it, right? It's more white, so it's more gas rich in there. So these different plumes, carry different stuff and go in different directions. We've had ash reported as far away as Captain Cook, right? And then down in Puna. So it just really depends on which way the wind is moving. This is a map showing in the oranges where most of the ash is gone, but in this kind of tan color, it shows where we've had reports of ash in Pele's hair during the eruption. So it depends on which episode you're at, how badly it gets. But the town of Pahala is usually square in the sites. So Pahala gets a lot of ash. They've had a lot of ash accumulations down there. So we also, a lot of our instruments out there, here's some of the solar panels running things. they're kind of hard to maintain because they keep getting buried in this stuff. So we get many feet of this pumice falls on these things. We have to get out there. Right now we have a Dodge Ram pickup that's stuck almost up to its roof in pumice. We've been digging and it just digs down deeper. So we're trying to seal it up so it lasts through the next eruption and then go out and get it again. But we've been working on this for a week, trying to get it out of this bottomless pumice. So we've had a lot of interesting issues in getting out there to survey. We have a lot of instruments over here, our gas measuring instruments. We have seismometers, we have cameras, we have lots of stuff up there. And it's been keeping us extremely busy. Homeowners run into this problem. If you're on water catchment, you really don't want a bunch of glassy hairs on your gutters, you know, so people can detach. It's really good to detach your pipes that come off your house from your water tank during the eruption so you don't get this stuff into there. But this is just here's on a car. You don't want to brush this off because it's like broken glass. It'll just scratch the finish of your car. So you have to be very careful washing things off. And you don't want to, we saw somebody in Pahala using a leaf blower to blow this stuff, but it's tiny little glass particles that you don't want to breathe in, right? So, you know, even an N95 mask, I mean, we all know, got those hanging around our house now, right? So those are pretty good at keeping the fine particles, you know, from getting in when you're breathing. You don't have to have the fancy big masks that we have. Here's the cameras. Here's putting out the new V3 camera out here. So it's a new site, and we're geologists. We use a lot of rocks. Use the natural resources, and it's because it's so windy out there. We have these big heavy tripods, but we've got to like build up rocks to hold them. And even then you can see the camera, especially the V3 camera, is buffeted by wind. So here's the little guy with its little eye. And these guys are putting these things in. We have a bunch of different cameras out there, some of them that don't report back to the network, but are the ones that we use for more accurate measurements and things. And yeah, here's digging stuff out. This is, everybody's gotten really tired of doing this. So here we got the Jeeps out to there, but recently after the last eruption, we got partway out to these sites and then sunk. First, the 2 Jeeps got stuck. And we got those out with the Dodge Ram, but then it sunk itself in when it was pulling the other ones out. So here's sampling some of the lava. And we use that to understand what the chemistry of the lava is. And the chemistry tells us the temperature. So that's pretty interesting. It also tells us something about what part of the magma chamber we're sampling, how long the stuff has resided in the magma body. So we can get a lot of information out of these little pieces of magma that we collect out there. We map all the time. We use photos, and then we can make scale maps. We have infrared cameras that we make maps after and during the eruptions. We don't fly during the eruption very often, but we'll fly afterwards. We have that radar satellite data that we're using. So we have a bunch of different ways of doing this. We also have one of the LiDAR units that we can actually take out there and measure stuff with too. This is just showing the thickness that we've measured up here, up through episode 38. So the thickness of lava, and the red is 140 to 160 meters. The green is 0 to 20 meters. The lighter green is about 40 to 60 meters. So that would be somewhere between 100 and 200 feet in that stuff. So there's a lot of lava. It's big wedge from the vents over across there. And remember, it's sitting on top of the lava lake, which is also molten inside. So early on in this eruption, the pressure from the lava lake was pushing down on the lid. The pressure from the new lava flows were pushing down on the lid of the lava lake, and lava lake stuff was leaking out over on this side. So we ended up with a bunch of interesting things. This is the cone that's building up on the top of the rim. So right behind the vents. So this cone is out there and it's building up on top of the cliffs out here. And if you look at this thing, it's gotten up, I think, what is it, 25-foot intervals? So it's like 150 feet high or something like that now. There's nothing like this in the geologic record. We can see back about 2,000 years in the walls of the caldera. And there is nothing like this eruption exposed anywhere. There's been a few high fountains that just leave a little layer of stuff like this, but nothing that's left a pervasive layer of material like this one is laying down. So it is a really unique eruption. What makes it unique? It's the number of high fountains that we've had up at the summit, and we only have had 3 other high fountain eruptions in the last 200 years like this. So first off, it's in a very small club of these eruptions that produce high fountains, because you got to have all these conditions met before you get one. But this one is huge in terms of what it's distributing and stuff. And Pu'u'o had more volume, but we're catching up to Pu'u'o really fast. And we're at episode 40 coming up, and there were 48 in Pu'u'o, or actually 47. So that was 3 years to get to 47. We're at close to, we hit 39 right on the anniversary, the 1 year anniversary. So we're moving fast on these things. And to get these kind of high fountain things dispersing this really light tephra all over the surface up there, it just does not happen very often. And they're spectacular, right? These are the kind of eruptions that define Hawaiian eruptions. There is a Hawaiian eruption. There are Strombolian eruptions named after Stromboli volcano, but Hawaiian eruption is a type of eruption. This is it. This is the type that it's named after, are these things. Yeah.
You mentioned earlier, half of the caldera is recharged since the 2008 collapse. Where
not recharged. What the hole has filled in about half of the volume. Yeah, and the nice thing about these vents is they're over on the southwest. And when we pumped up the summit last year, we pumped up the whole southwest side of it. So one of the ways this could end is by having what happens each time after each eruption, the vents are getting higher and higher, and the pressure is gradually increasing. And we're measuring that pressure increase using GPS instruments. We use a different set of instruments to measure the deep pressure increase. We're measuring both the pressure on the deep chamber and the pressure on the shallow chamber with time. And the shallow chamber, even though the peak inflation is declining, the inflation we measure, or the pressure that we measure with the GPS instruments, shows it's been increasing during the last year. So what that means is that's due to the fact that the vent elevation is climbing. This is what happened at Pu'u'o. The vent got too high. The pressure was too great. It found something weaker. It broke open the rock and moved down to Kupainaha, a kilometer down the rift at a lower elevation, and came out continuously. Mauna Ulu, the vents collapsed and it started coming out continuously.
All right, that was Dr. Ken Hon from USGS with his talk this afternoon. The highlights there, so really fascinating to hear all those details, see some new graphs, hear about all the stuff that's been lost and buried and renamed and all that. So lots to talk about in the upcoming weeks and months here. I think I'll switch us back here to our live view of the cameras. As you can see, there is another overflow occurring here from the south vent as we speak, showing that we are approaching that next window of eruption that USGS says will come from Saturday to Tuesday this week. Lou, any other thoughts?
It was a good presentation by Ken again, which, like I said, we've seen so many of them, but that highlighted a lot of things in there. One of the ones I picked up on was how truly he is excited about this episodic eruption that's happening and how it's making history. You can sense it as you listen to his voice, especially for us that talk to him on a regular basis over here. There was some things in there that we haven't heard, the trucks getting buried, the cameras getting buried. Pretty amazing. It was a good presentation. I'm looking forward to the rest of Volcano Awareness Month, and he's got a great crew, and I have a feeling that the rest of them all have the same feeling going on here.
Yeah, absolutely. Yeah. So excited that even our ASL interpreters had to struggle to keep up here a little bit.
Wasn't me this time, Dano.
Or me, which that's my thing for sure. Talking super fast. So all right, here's a live view at the ongoing eruption. As Ken said, there it is, magma coming from deep inside the earth, pouring right out. It is an eruption, maybe not the one you wanted, but this is the start of it. All that degas lava getting pushed off until we have a small enough cap over the fresh stuff that it can come shooting out. So we'll all await that eagerly over the next week here. Keep an eye on our regular channels, Hawaii Tracker on Facebook, all of our other social media channels as well. We're posting updates as we have before, as much as we can.
I do have some
And
super chats in here as well, some
yeah,
donations that
right.
came through. Let me drop
So yeah,
this in here. I got two in here. Two from Raven S, a $10 and a $20 over on our donation platform. Thank you. And one from Robin O over on our platform as well, $20. Mahalo, Robin. Appreciate it. You guys are great. Thank you again to everybody who supported us all last year and helped, as Dane likes to tell us, keep the digital doors open around here. And looking forward to a great 2026 with you all.
yeah, for sure. I appreciate all of everyone's support and ongoing here. And so before we wrap it up, one final last thing here. I did forget to show our banner at the start here for you, Lou. So I'm going to put it on here right now.
Thank you.
And you can have something for later on for us to complete our work here. All right, guys. So from our nonprofit, Hawaiian Volcano Education Resilience Institute, HVERI, for Dane DuPont behind the scenes, Lou Atori, our ASL interpreters, Dano and Kerry. I am geologist Philip Ong. We'll be back with you guys next week. Until then, aloha, everyone.
Go, Phil. Go, Phil.
There he is. All right.